Hi, and we're back. This is ET370 Lecture 8, Part B, and here we're just going to talk about using an NMOS in a practical situation. I'm going to go over three versions and then look at a simulation. And so this first version is very similar to the tester circuit we had. So imagine you have 10 volts across this load resistor and your MOSFET, right? Remember the MOSFET's acting like a switch. If I close the switch, current can flow from the 10-volt source into my load and then through to ground, okay? And so imagine I have some input voltage like an Arduino that can go from 0 to 10. Well, I know an Arduino can't go to 10, but let's say you can go from 0 to whatever supply voltage is, this is, and let's say it's 10 volt. And so you're going to bounce between cutoff and triode, where triode is like the fully on shorted case of this MOSFET, right? Now, what's the problem though? The problem is you would need to reach 10 volts and not just 5 volts to really turn on this MOSFET, right? Now they do sell logic level MOSFETs, so those are common, but if you just use a regular MOSFET here, this Arduino here that's at 5 volts or maximum 5 volts wouldn't be able to fully turn on this switch, if you will. Now, what's a simple solution if you want to get this gate source voltage high? Well, what you could do is add a little helper NPN here and have a pull up resistor, okay? And so then what you do is you have your Arduino, which goes from 0 to 5 or 0 to 3.3, and drive a little NPN so you can just pull a little base current. And let's try to imagine what's happening. When the input voltage is 0, okay, what happens? This NPN is off. So this is like an open circuit. If this is an open circuit, this gate voltage actually jumps up to the 10 volts, fully activating this MOSFET because of the pull-up resistor, and you get your triode mode and the current flows, right? And it flows from the voltage source down through the load, okay? Now, if your VN is at 5 volts on, then the NPN is in saturation, or this is turned on. What you've done is you shorted the ground or the gate to the ground, right? And so in that case, the NPN now shuts off. So notice the input logic is reversed, right? Low voltage here at the input means that the NMOS is going to be in fully active triode mode. Whereas a high voltage at the Arduino input, what's going to happen is that this NMOS is going to be cut off, right? Okay. Now, one issue with this implementation is if your VS is too high, right, then your VGS, because this jumps directly to whatever VS is, this is going to get too large. And if you remember from our previous lecture that and I'll just show it right here. I have the data sheet. The data sheet here says a VGS has a plus or minus 20 volt for this specific chip here, right? And so let's say you had a VS that was higher than 20 volts, you would break your MOSFET. Okay, so what's a solution to that? So a solution to that would be this implementation. It's nearly identical. The only difference is maybe you could put a Zener diode here, right? And so let's say your voltage now, your voltage source was 100 volts instead of 10. Obviously, if you went to this implementation, your gate source voltage is going to break, right? Because this is going to go to 100 volts, surpassing that 20 volt limit, right? But if you set your Zener diode breakdown voltage to, let's say, 20 or 15 or something within the safely operating range of this MOSFET, you'd be good. And so let's imagine what happens when this low voltage occurs at the input. Okay, the input is in cutoff, and the Zener diode will limit the VGS. Now, is it inefficient? Yeah, because you're shunting current here, right? But at least it's protecting your gate voltage, right? Now, if this is high, then then what happens now? This is shorted, right? And you're just pulling a little trickle current, but essentially this gate is now 0, and then this is off, right? Now they do sell MOSFET drivers, right? But if you're just trying to implement something simple like this, then this might be a practical implementation of the MOSFET. Let's go to the simulation and just check out these three different cases. Now, I want you to remember, this is normal logic, and these two are inverted logic. This one here is going to have an assumption that the source is at like 10, some medium voltage that's not going to break VGS. And here you have the Zener diode to protect the gate source voltage. So this can be a little bit higher, right? Or a lot higher. All right. So let's switch over to the simulation and check it out. Okay, and with all my videos, if you just go to the description, you can go and actually click the link to the simulation, play with it yourself. So I'm going to run this, okay? And notice here on the far left, I just have my normal MOSFET going. And so I can control the gate voltage with this slider over here. And if I slide it up, you can see it activates, right? And I'm going all the way to 10 volts and going down to 0, and you can see on and off, yay. Okay, and that's normal logic, non-inverted logic, right? Now the middle one here, I have the helper NPN, and we will be using this later on in the last lecture here. But I have this controlled, or sorry, limited to 0 and 5 volts. So this gate voltage is starting out 5 volts and goes down to 0. Now notice the inverted logic, okay? When the gate voltage is high, the NMOS is off. When the gate voltage is low, then the NMOS is on. And notice I don't have a Zener diode, but now the gate voltage here, you can see it actually jumps all the way up to 10 volts with this pull up resistor, and the load turns on, okay? Now the last one here, I have the gate, voltage source jumping all the way up to 100 volts here. And notice I again have the gate only going from 0 to 5. And when it's at high, I'm shorting the NPN essentially, and this gate voltage is pulled low and the NMOS is off. And when I go low here, then the Zener diode takes effects. This gate voltage wants to jump up to 100 volts, but the Zener diode is limiting that, right? Now, yes, there's current being pulled through here, but because you have a 10K, it's just a trickle current that's going through here. But yeah, these are kind of inefficient because you got currents kind of flowing in the off and on case that are not contributing to your main flow. But this worked, and it protects your gate source voltage. So now the maximum gate source voltage is going to be 20 volts, okay? All right, well, I hope these the simulation, these videos helped, and I'll look forward to seeing you in the next part of this lecture series.